Hello everyone, I am Dr. Krishnasree working in VNR Engineering College. Today I would like to explain about Class AB, Class C power amplifiers. With the previous videos, I have covered introduction of power amplifiers, the working of Class A, Class B and the comparisons, their working and derivations of conversion efficiency in all these cases. Now I would like to explain about Class AB power amplifiers, Class C power amplifiers and the required necessary supporting components in power amplifiers. Today the contents covered are Class AB power amplifier, Class C power amplifier and the heat sinks required for the power amplifiers. So before introducing the Class AB power amplifiers, let us see Class B power amplifier and what is the disadvantage in it and why we are going to Class AB power amplifiers. Let us take the Class B power amplifier, whether it is a transformer coupled or whether it is a complementary symmetry coupled. Then first Q point is selected on load line at cutoff. So cutoff, the Q point will be VCC, 0 when you are considering this parameter as VCE versus IC, and this one will be the saturation and the remaining portion will be the active. So because whether we are taking cutoff on cutoff the load Q point, this is our Q point which is VCC, 0. So due to this, if you apply any input signal on this one, it is going to projected onto this output. Only one portion will be resulted at the output. That is, it is working in the only one half cycle, whether it is a positive half cycle or negative half cycle. That's why we are taking two Class Bs. Suppose if I take a complementary symmetry amplifier, so here one is NPN and another is PNP. So both are connected together and their emitters are connected together. The VCC is taken at this point. Here minus VCC is taken and the input is provided at this point. Output is taken at this point. So whenever you are applying a full half cycle, in the positive half cycle, this transistor Q1 is on and the waveform generated here, I am just writing the output waveform. So if I take here, when it is in the positive half input half cycle, output Q1 is on and here the voltage is produced. And in the negative half cycle, Q2 will be on and output will be produced like this, like this, like this. But if you look at this crossover points, there is some gap because of the cut-in voltage of both the transistors. So V cut-in voltage of silicon is 0.7. Similarly here it is minus 0.7 for PNP transistor. So top transistor is NPN, bottom transistor is PNP. So because of this lag or because of this some delay caused due to the cut-in voltage, there is a distortion is involved here, which is known as a crossover distortion. So here there is a lag. This crossover distortion is because of the both the transistors will whether on in the positive half cycle or in the negative half cycle. So that's why this crossover distortion appears in Class B power amplifiers because of the two sections, upper section and lower section, are making the output waveform combining both positive and negative half cycles, and crossover distortion will be arises due to this. So we don't want the crossover distortions because for a given input, so we want the output only it should be amplified in terms of current and voltage, but not the shape should not get distorted. So this is the input voltage, this is the output voltage. To avoid this crossover distortion, we have to introduce some additional components, so that additional components in the original Class B power amplifier. So for what is the reason, what the need of that components? So positive half cycle, NPN should get 0.7 voltage, and for the PNP transistor, it should get the minus 0.7, so that it can avoid this lag in the changing over from positive peak to negative peak. So for this, what we have to do is, so take the, again this one, so I am connecting, so both the emitters, so this is PNP emitter and NPN emitter together, and here I am considering the output with VCC and minus VCC, and I am applying a input signal over here. Okay, so whenever the positive half cycle you are applying, whenever a positive half cycle is applying, if I connect some resistors from VCC to ground or minus VCC with a variable, whenever this input signal, it is crossing less than 0.7 VCC, some equipment should provide that 0.7 as a complementary or as a supplement to it. So this voltage R1, R2, R3, it should be such that the drop across these two bases should have 0.7 voltage. So it is applying from plus minus a 0.7 voltage. So before reaching the 0.7 voltage, so output is, instead of generating from here, now it is generated directly, because already 0.7 voltage it is provided. And whenever it is in the negative half cycle, so this negative half cycle, through this minus VCC, it is producing a minus 0.7 voltage, and without having any lag, it produces like this. Otherwise, it is something, there is a lag is happened and it will produce like this. So instead of that one, you are getting a waveform by eliminating that tilt, or by eliminating some curved portion, which is a crossover distortion. Then this amplifier is known as class AB. That is, your transistor Q1 is conducting before also. That is something I am starting before itself, and Q2 also it is starting before itself. So like this, and if you combine these two, then crossover distortion will be avoided. So this class AB, Q1 is operated more than 180 degrees conduction, because previously before conduction also there is a 0.7 voltage, it starts conducting. Q2 also, before getting minus 0.7 from the input, it is getting through this extra network. So Q2 also is operating for more than 180 degrees. It is in the positive half cycle, it is in the negative half cycle. So that's why it is neither A, because class A will operate from 0 to 30-60 degrees, class A. Class B operates from 0 to 180 degrees. Now it is more than 180, less than 360. So Q1 and Q2 both are operating between 180 degrees to 360 degrees. Here it is between 180 degrees to 360 degrees. So that's why it is a combination of A and B. That's why it is known as class AB. When coming to the operating point, how the operating point should be selected? Suppose if you select, this is cutoff, because it's more important to select the operating point. Suppose here if I select Q point, which is VCQ, ICQ, which is for the class A. Now if I select here, it is cutoff. The operating point will be, Q point will be VCC, 0. Now the operating point should be not in this portion, but it is instead of this portion. Okay, this is the portion of Q point, which should be greater than VCQ and less than VCC. ICQ also greater than 0, 0 milliamperes, and less than the middle point ICQ. So now the operating point, we can say that operating point of AB, it is active region in between to cutoff. So it is a hybrid power amplifiers, a combination of A and B. And efficiencies also, it is more than class A, that is more than 50%, and less than 78.5%. So when you know what is the what is the operating point you are selecting, so the characteristics also in between class A and class B. So that's why the name is indicated as class AB. So these are the major important things. So what is an advantage? It eliminates crossover distortion. Eliminates crossover distortion. So if you know the operation of class B, efficiency derivation of class B, then the remaining thing will be elimination of crossover frequency as well as increase of frequency. Now you can see here the Q point is, it is active load line. So it is in between, Q point is on active and it is on saturation. Now the new Q point is this one. So if you apply a signal, so only some portion will be eliminated, but all the remaining portion will be appeared at the output signal. It is very contrary to class A. Class A means the complete signal. Class B means only half signal. But class AB means it is combination of both the signals, that is this one. So for full cycle like this, it adds only little bit of distortion in the input signal, but it avoids crossover distortion. So the class AB power amplifiers will improve the crossover distortion, or will eliminate the crossover distortion and improve the faithfulness of the input signal appearing at the output. Then coming to the class C, this is the third class of amplifiers other than class A, B, and combination of A, B, class AB, and the third combination is class C power amplifiers. Here if you take the Q point of class C on the load line, it is below cutoff. Below cutoff, that is the conduction angle of Q will be, it is not complete 360 degrees, not complete 0 to 80 degrees. The conduction angle will be, it is between 0 to 180 degrees or less than 180 degrees. That is only 1/4 approximately, only less than 1/4 time. This one is in the operating mode. That's why it consumes less power. So here if you look at the circuit diagram, so it is taking generally some through L and C circuit, we can use the load. Otherwise simply, so instead of this one, we can add the load also. Here the component minus VBB is applied at the input signal. So by applying the negative voltage, what it is done, the operating point generally maximum of VCC and minimum of 0. But here it is introduces, instead of VCC, it just deeply down to minus VBB. That's why if you look at this Q point, so which is already it is in the negative portion, that is less than the 0. So it is almost minus VBB for VCE, and IC is somewhat negative value, negative ICQ. So this is making your transistor will go into the cutoff or deep cutoff. Deep cutoff means less than 180 degrees it conducts. Suppose if you apply input signal like this, so you can see not the complete cycle, only one portion it is appearing at the output. So the conduction time of the transistor will be reduced enormously, and the remaining power it is given to the load. This is the load. So that's why efficiencies will be improved a lot. Because of this, conversion efficiency will be almost 95 to 99%. Because for a small amount of time, so this is 0 to 180 degrees, how much time you are going to conduct, how less time it is, the more will be the efficiency. So this is known as class C, and below cutoff is the operating point, efficiencies are increased. But only the disadvantage is output is not at all resembling the input. Not at all at any point of time, because only one small portion of the time it is used. So this class C power amplifiers, wherever we require larger efficiencies and more powers, but the input is not resembling the output. So if you look at the inputs, if I draw here, how the input and output will be. Suppose if you provide an input like this, so output will be only some half portion. This is input signal, and output will be only this much it is appearing, and all the things is going to be 0. Again in the next half cycle, so it is having a very small portion. This is the output. So we cannot get the input as it is in the output. So signals where we require an amplification but do not require any resemblance of the input, that is the what is that no need to get back our complete input signal as output, then we can take this class A power amplifiers. For example, carrier multiplication or carrier amplification in analog communications. So where preserving the carrier does not required, because carrier is not carrying any information, we can apply this class C power amplifiers for carrier amplifications, because carrier must be very strong and message signal should be preserved. So for message amplification, class C cannot be used, because message can be preserving. It has to preserve its shape. Otherwise, we are going to lose the information at the output. So messages class A and class B will be used. For carrier amplification, class C will be used. So the efficiency is required. A very big analysis, because class C power amplifiers, the output is not going to have its complete signal. It's very difficult to derive in one attempt. So that's why power amplification, classification, conversion efficiency, it requires high frequency analysis and so on. So directly conversion efficiency has been mentioned as very near to 99%. Then coming to how these common power transistor part numbers are available. So generally these popular power transistors will have a numbers with starting from 2N, TIP, IRF based on its common characteristics. These are the widely used common power transistors. If you look at, I'll just introduce few numbers. 2SA1 943. What are its specifications? So it is a high power PNP transistor used in heavy duty audio amplifiers, especially in the output stages. As I have told already, any amplifiers, whether it is audio amplifier or music amplifiers, first 3-4 stages we have to use power voltage amplifiers, and the last stage we have to use the power amplifier. So another importantly widely used power transistor is 2N3055. It is an NPN transistor as a BJT transistor, normally used in linear amplifiers, and it is very strong or stubborn, having a stubborn case. It is nothing but it is having a TO3 metal case. It handles up to 15 amps and 60 volts. So the power generators are 15 into 60 volts, like almost kilowatts power we can generate. Another is tip 31C, tip 41C, 42C, 32C. All are having a tip as the basic class of family of amplifiers. So different numbers will provide you different purposes. It is a general purpose NPN power transistor. It is popular power transistors. Even its rating will be 100 volts and 6 amperes. You can see from one transistor to another transistor, the voltage ratings and current ratings are going to differ. And NPN and PNP also another important difference. And BD 139 and 149. So these are complementary symmetry pair. So what does the complementary symmetry mean? So both the transistors will have the same beta. That's why it is known as similar. Why we should require similar? Because there should be a mapping for the current flow or for the voltage amplification. So beta is very much necessary. Why? IC is equal to beta IB. If one transistor is amplifying its current by beta times and another transistor with a different beta, then combining the output for the positive half cycle and negative half cycle is not going to happen. So finally this IRF 1010, it is N channel MOSFET, power MOSFET amplifiers. So different amplifiers, different transistors will have different shapes like TO3 package, TO220 package, that is a metal one or a plastic one or a ceramic one. Their numbers is going to change. And the last number C is indicating it is a commercial grade. Commercial grade means normal operating temperatures. Otherwise, for military grade, different number will be used. Look wise, how they look like. If you see, this is a 2N3055. Here you can see the name. And here it is for less powers, this kind of smaller in size. And if you look at, there are only two terminals, base and emitter, and collector terminal will be its complete case. And for a less powers, this kind of TO39 package will be used, that is tip 3055. First one is base, intermediate is collector, and final is the emitter. If you look at the size, is going to be differ from this size to size. So this more in size, more the power. And if you look at this one, it is MJ series 101Z. And the sizes will differ, and these two things will be used to connect this power transistor onto a base or onto a PCB. We have to use some screws through this one, and then two terminals, only two pins are coming from here. These two pins has to be soldered on the PCB. And if you take, this is a TO39 package, and it is having a cup kind of structure and having three terminals. So here the one terminal in the middle, it is capacitor, it is connected always to the case. Why it is connected to case means this collector, there is a heat generated, we have to pump the heat outside, we require a larger surface area. That's why if you connect collector to the large surface area, power transistors, this collector area will be enhanced or area will be enlarged. So because of that only, always collector pins are connected to the cases. If you look at this, this is front view, and if you turn the power amplifier, you can see the two terminals. Normally transistor will contain three terminals, but other terminal we are fixing this transistor onto a metal surface, so that still this collector area will be still enlarged, so that the powers generated or temperatures generated will be dissipated into the free space very easily, so that the transistor will be protected. So here what one point is observed, the based on the powers, if power is more, if power increases, its temperature generated also increases. Okay. So the generated power should be transferred to the load. Complete power, if it is not transferred to the load, there is a mismatch with the powers. That is, power generated should be equal to power transferred. If there is a difference in this power transfer, then the remaining power is going to appear as a heat. The result is heat will be generated at the collector. So collector is a very important area. It has to be kept very cool all the time. So there should be an extra arrangement we have to use. That arrangement we call it as heat sink. To dissipate this extra temperatures generated at the collector into the free space, we call it as a heat sink. That's why it is similar to our water sinks in our kitchens kind of thing. So the water which we need to pump out of our usage, that is going to be collected at the one point, we call it as a water sink. Here the extra heat should be collected at one point and it should be dissipated into the free space. It is almost sinking the heat, we call it as a heat sinks. So if you look at here, heat sink having one aluminum area, because it is a mechanical device which is used to dissipate the excess heat generated at the collector junction into the free space. So this is the bottom of the heat sink like this. And if you take the vertical photograph, if you take the horizontal photograph, then it looks like this. So these are known as fins. So because of this fin kind of construction, this bottom side of your heat sink, there will be a power transistor should be connected. And power transistor collector is connected to this heat sink. Collector area is increased to this complete body of the heat sink. The more is the power, the bigger should be your heat sink, because the more is the fins, the more is the capability of dissipating or radiating the excess heat into the free space. Other kinds of constructions of heat sinks I will show you. So it is a round heat sink, round one. It is a press type. If the transistor is in the TO39 package like this, so we can press this heat sink onto this one. So like how we are wearing a cap on our head. So it comes around the complete case of, that is normally our transistor. I have already shown here just this type of transistors. Then we require heat sink on the one. So we have to press this kind of heat sink from the top of your transistor body. So you have to press it. Then this is the heat sink in another direction. So where here you can see the holes. So here we have to press our transistor, keep our transistor through some 2 holes, and these are the 2 pins. These 2 pins should be soldered on the heat sink body, and these are the screws where we have to fix it on the body. This is for smaller transistors, this kind of very small. On both sides there are fins are available, and you have to keep your transistor in the center. And this is another type of construction. This is aluminum construction. So with the TO3 transistor. TO3 transistor means the transistor will be of this type. So you have to fix the transistor at the middle, and the heat will be radiated through these fins. Something like big ears for an elephant. So you have to use these extra ears to pass the heat into the free space. These are the references I have used to prepare my PPT of this power amplifiers, which contains class A, B, class C and the heat sinks sessions. Thank you very much.
Like, share, comment and subscribe VNR Digital Learning Resource YouTube channel.